Hello and welcome to the Logic of It All. In this video, we will talk about the spanning trees. So let's start with the definition. What is a spanning tree? Imagine we have a graph G that is connected. So it has some nodes and it's connected, which means that for every two nodes that you pick, there is at least one path between them. Now, what we want to do is, if you imagine this being a network, we want to keep the same nodes and we want to keep the graph connected, but we want to reduce the number of edges as much as possible. And if we do that, we end up with a tree T, which we call a spanning tree of the graph, where T has exactly the same vertices as G, and the edges of T are chosen from the edges of G. So basically T is created by removing some of the edges of G while we maintain the graph as connected. Okay, so here's an example. If you look at this graph on the left, it's obvious that it's connected, but if you think about it, we can reduce the number of edges while we keep the graph connected, right? And if we do that to its limit, what we end up with is a tree where it has exactly the same 5 nodes, 5 vertices as our graph, but it's a tree, which means it's connected, but it doesn't have any cycles. And there is more than one way to do that, but this is one of the spanning trees of this graph. So you see the same set of vertices, and the edges in the tree are a subset of the edges in the graph. So in other words, we create the tree by removing the edges from the graph as long as the graph remains connected. Okay, so this is the concept of a spanning tree. As I said, there are different ways that you can do that, and all of them are equivalent in terms of the number of edges that they are going to have at the end. However, the problem becomes more interesting if the graph is weighted. Okay, so in that case, each edge has a weight associated to it. And what we want to do is we want to find a spanning tree where the sum of the weights of the edges that are remaining is minimum. Okay, so if you think about this network that we have on the left, where we have these different nodes, imagine those are different cities, and they are connected with different roads and so on. Now, what we want to do is we want to keep the network connected. So we want to be able to go from every node to every other node that we want. But we want to minimize the total of sum of the weights. Now, if you imagine weight here in this example could be the cost of maintaining the roads, right? So we want to minimize the cost by removing the edges that are costly. Okay, and in that case, what we end up with is called a minimal spanning tree. Okay, so first of all, in this context, your graph is weighted. Still, what you want to do is you want to remove as many edges as possible. Again, you want the remaining graph to be connected, and it's not going to have a cycle, so it's going to be a tree. But on top of all of that, we want the sum of the weights of the edges to be minimum. That's why it's called minimal spanning tree. Now, if you think about that, this is not as easy to do as the case where the graph was not weighted. And to be able to do this, we are going to introduce two different algorithms named after people who created these algorithms. The first algorithm that we are going to see is called Kruskal's algorithm, and then the second one is Prim's algorithm. And as you will see, both of them are going to give you a minimal spanning tree of a given graph, but their methods are very different. Let's start with Kruskal's algorithm. Okay, so what we do is we start with the tree T to be all the vertices of the graph but no edges. So basically it's not a tree yet, right? But we keep all the all the vertices without any edge. And then we have a counter that tells us when to stop. We initialize the counter to be 0. And then we go to a loop and repeat the loop until for as long as count is less than n minus 1. N is the number of vertices in the graph. What we do is at every iteration, we find an edge in the graph with the lowest weight, and we delete that from the graph, and we look to see if adding that edge to our tree creates a cycle or not. If it does, we just throw that edge away and go to the next iteration. But if it doesn't create a cycle, we add that to the tree. And we repeat this until count becomes equal to n-1, and then we stop. So here's an example. So in this example, we have this graph with 6 vertices, and you see that obviously the graph is weighted. Now what we want to do is we want to apply Kruskal's algorithm to find a minimal spanning tree for this graph. So here we go. At the beginning, as we said, we start with all the vertices. So let me do that. So we have 4, 3, 2, 6, 1, and 5. So this is my T, and this is G. And now, and then we initialize our counter to 0. And we go to the loop, and we are going to repeat the loop for until for as long as count is less than. So my condition is count is as long as count is less than n-1. Here my graph has 6 vertices, so n is 6. 6 minus 1, 5. So for as long as count is less than 5, I'll repeat this. Now, here's what we do. We look at the graph, and we pick the edge with the lowest weight, which is the edge connecting 4 and 1. And we look to see if I add that edge here, whether it creates a cycle or not, which it doesn't in this case. So we add that here. And we remove that from the original graph. Now we repeat, because count is now 1, which means it's still less than 5, so we repeat. We go back to the graph. Now this edge is removed, so now we look and find the edge with the lowest weight, which is this guy here, connecting vertex number 1 to vertex number 2. We verify whether adding that edge creates a cycle in T, which it doesn't, so we add that here, 2. We remove that from the graph, we update the counter to 2. And repeat, right? Because count is still less than 5. So now the next edge, we have 2 choices, because we have this edge connecting 4 and 2 with the weight 3, and also this edge connecting 3 and 2 with the weight 3. Let's go with this one first. So I pick this one. But when I try to add that, I realize that that creates a cycle. So I remove it from the original graph, but I don't add it to my tree because it creates a cycle and it's not going to be a tree anymore. And I don't increment the counter because I didn't add any edge to my tree. And then I go to the other one, and that's connecting 3 to 2. That doesn't create a cycle, so I go ahead with that, remove it from the original graph, and then update the counter to 3. And then going with the same kind of approach, this is the lowest weight now. Adding that doesn't create a cycle, so I do that, remove it from the original graph, update this to 4. And I have one more iteration because 4 is still less than 5, so I'll do one more iteration. I have what's left is 5, 7, 8, and 9. 5 is the lightest one, but if I try to connect 3 and 4 with that edge, I create a cycle. So I remove that from the graph, but I don't add it to my tree, and I don't update my counter. Next iteration, because counter is still less than 5, this time 7 is the lowest, so I remove it from the original graph, and I can include it here because it doesn't create a cycle. And I update my counter to 5, and now I go to the top of the while loop. This time 5 is not less than 5, which means I stop, and what's created here on the right side is my minimal spanning tree. So you see it has the same set of vertices as the graph. It is connected, and it doesn't have a cycle, so it's a tree, it's a spanning tree. And you can verify that it's minimal, which means that there is no other spanning tree where the sum of the weights is less than what we have here. And what we have here is 4 plus 1 plus 2 plus 3 plus 7, and that is 17. So 17 is the minimum that is possible for this graph, for a spanning tree. So that's Kruskal's algorithm. And the way that you are expected to do this is writing down those iterations in a table. So on the first column is the value of count. On the second, you see that sometimes in some iterations count is not increased because we pick an edge, but we don't add it to the tree because it creates a cycle. And then on the second column, we write down the edge that we selected on that. And then on the last column, we say whether or not that edge is added to the tree. And that depends on whether or not it creates a cycle. So that's Kruskal's algorithm for you. And this is the way that you can write down the whole process. Now, the second algorithm for finding a minimal spanning tree of a weighted connected graph is Prim's algorithm. Now this works differently. So what we do is we start with a tree with one vertex. Instead of picking all the vertices but no edges as we did in Kruskal, here we pick only one vertex and then we expand that one vertex into a full tree, a full spanning tree. So one vertex, and then the first vertex is arbitrary. You can start with any vertex that you want. And then we starting with this one vertex, we expand that, as I said, one edge at a time until it grows into a full spanning tree. And the way that we do that, it's best that I explain that in the example here. So this graph here, we want to find one of its minimal spanning trees, but this time we want to use Prim's algorithm. So I start with a vertex, let's say 4. Any vertex will do. And what I'm going to do is I'm going to use blue for the vertex that I have selected and red for the vertices that I have not selected yet. If that is clear. Okay, so I've selected 4. Now what we do is at each iteration, we look at all the edges that connect the selected part, the blue part, to the red part in the original graph. Okay, now here, how many edges do you see in the graph that connect 4 to one of the red ones, right? You see this one, you see this one, and this one, right? So I have 4 options. Now between those, because we are looking for a minimal spanning tree, I pick the one that is the lightest. It has the lowest weight, which is 1. So I connect my node to here. Okay, and now this is also blue. Okay, now next iteration. Again, counter, now counter is 1, right? Now, the blue part now is 4 and 1, the red part is the rest of it. We do the same thing. We look at all the edges that connect a blue vertex to a red vertex. Now, what are those? Let me clear this up and do this again. So all the edges that connect either 4 or 1 to the rest of the vertices. So we have this one here, this one here, this one connecting 1 to 5, this one, and this one, right? So these are all the edges that either connect 4 to one of the red vertices or 1 to one of the red vertices. So between these 5, I again pick the one that has the lowest weight, which is this edge here. So I expand my tree again this direction, and now this is also part of my tree. So this was 1, this is 2 now. Okay, so you see I started with one vertex and step by step my tree is growing and now I have 3 vertices and 2 edges. Now, next iteration, same story. Look at all the edges where one side of the edge is in the blue and the other side is in the red. So let me find those here. So this is one, this is another one that connects a blue to a red. This is another one that connects a blue to a red. This is another edge that connects a blue to a red. So is this one, and that's it. These are all the edges that connect a blue vertex and a red vertex. Now between these, the one on the left here, that has the lowest weight, so that's the one that I pick for my next iteration. That means that now 5 is part of my tree. The weight was 4. Now it's connected. Now my tree has 4 vertices, so I have 2 more steps to go. Now again, starting over in the next iteration, I need to look at all the vertices in the original graph that connect a blue vertex to a red vertex. So this is one of those edges, this is another one of those edges, and here's another one. And that's all. So I have 3 edges to choose from, and the one that has the lightest weight is the one that connects 2 and 3, this edge over here. So I pick that as my next choice. Oh, wrong color. So I connect 2 to 3, and now 3 is part of my tree, so I'll change that to blue as well. Okay, so we're almost done. The weight on this one is 3. We're almost done. Now in the next iteration, you notice that my tree contains all the vertices except this one on the right, vertex number 6. And now if I want to look at all the edges that connect a blue to a red, I have 2 of those, namely this one and this one. And here I pick the one that has the lowest weight, which is 7. And I connect 2 to 6 with weight 7. And now 6 is also part of my tree, which means that's the end of the algorithm. Okay, now note that in this algorithm, I don't need to worry about creating a cycle, because at every step, what I'm looking at is the edges connecting a red to a blue, and those edges are not going to create a cycle. So you don't need to worry about the cycle, you don't need to check that. Just look at every iteration, look at all the edges that connect the blue vertex to a red vertex, and between those, choose the one that has the lowest weight until you have a full tree. And that's your minimal spanning tree using Prim's algorithm. And again, we use this table to write what we did in a more formal way. So you have your counter on the first column. The second column, set of vertices remaining, that is the set of red vertices. And then the last column, we emphasize which vertex we select at each iteration and which edge we select. So this is the new vertex that is added, and then this is the edge that's added to the tree, and so on. Okay, so there you have it, 2 algorithms for finding minimal spanning tree, namely Kruskal's algorithm and Prim's algorithm.